The relativity of simultaneity strongly hints, in fact, almost necessarily requires, that motion, speed, must be affecting time itself. The rate at which time passes must be affected by motion. That's the only way that we really can conclude, as we have already, that simultaneity depends upon your perspective. I mean, in the treaty signing ceremony, if clocks on board the train agreed with clocks on the platform, then everyone would agree on what happens at a given moment. Everyone would agree on whether the president signed at the same moment. But they don't agree. And so clocks that are moving relative to each other must tick off time differently. Now, for us to make that idea precise, to us to really understand how it is that motion affects the passage of time, we need a way of measuring the passage of time. We need, of course, a clock, right? Now, you can use, for all that we are talking about here in relativity, you should feel free to use any clock that you like, right? Your favorite Rolex, your favorite grandfather clock, any clock that you'd like to use. I, however, am going to make use of a special kind of clock that's quite unfamiliar, but as you will see, it's a very powerful kind of clock for assessing the effect of motion on time. So I should spend just a moment addressing the issue of what is a clock, right? So what is a clock? A clock is any physical system that undergoes cyclical repetitive motion, and it does that cyclical motion. It undergoes those cycles in a uniform way, right? So if you're talking about using the Earth as a clock, the Earth spins around its axis in a uniform way, and we use that to say every time it goes around once, that's a day. We can talk about the Earth in revolution around the sun, right? It does that in a fairly uniform cyclical way, and we call each revolution a year. And on a more standard wristwatch, if you have, well, I should say one of the old-fashioned ones that has a second hand that's sweeping around, it does that sweeping motion cyclically, sweep after sweep after sweep, and we call each of those sweeps a minute, right? So that is what a clock is, conceptually. The new kind of clock that I'm going to introduce has that same kind of feature. Cyclical motion, a cyclical process happens over and over again, but the process itself is a little unfamiliar, because the kind of clock that I'm talking about is called a light clock. What is a light clock? A light clock is a contraption in which we have two mirrors that are facing one another, and a ball of light will bounce in between them. And every time the ball goes up and down, you can think of that as tick-tock, right? Tick-tock. The ball is just going up and down. So let me show you a quick visual of this kind of clock, this light clock. There it is. So every time it's going up and down, so let's do it. So it goes tick-tock, tick-tock. It's regular cyclical motion that you could use to measure how much time elapses between one event or another. The reading is up there at the top of this light clock. And what I want to stress at the outset is that this light clock, however unfamiliar it is, right? It is unfamiliar. You cannot go down to Walmart and buy one of these light clocks. But conceptually, a light clock is no different from any other kind of clock, which means any conclusion that we reach about the nature of time that makes use of this light clock as an intermediate part of the reasoning, that conclusion applies to any clock. It would just be harder to reach that conclusion with a clock that had a more complicated internal mechanism. Because, as I'll show you in a moment, the beauty of the light clock is that because the mechanism, the tick-tock mechanism, is so simple, we can very easily determine the effect of motion on the passage of time. Okay, so to do that, I'm going to want to introduce a second one of these light clocks, because I'm going to want to compare the rate at which time elapses on one compared with the other, not when they are stationary, as they are here, but I'm going to want to set one of them into motion. Actually, before I do that, let me tell you what you're going to see, just to prepare you, because this is a great, wonderful result that we're going to find, and I want you to be fully prepared for when it comes. Imagine in your mind that I have one of these light clocks, okay? And I'm going to walk with it. Now it's in motion. From your perspective, think about the trajectory that the light will travel, right? From your perspective, the light will start here, it hits the top of the mirror here, and then it hits the bottom mirror here. So from your perspective, the light will have undergone a diagonal up and a diagonal down trajectory as I'm walking with the light clock. So I'll show you this in a moment, but let me just address one quick question. First, you might think, well, if you're walking with this light clock with the two mirrors, won't the ball of light sort of miss the top mirror because you're moving as you're going along? Answer, absolutely not. What's the argument? The argument is simply this. From my perspective, okay, I'm undergoing constant velocity motion, right? Same speed in a fixed direction, which means, from my view, I can say that I am stationary, and it's you and the rest of the world that are rushing by me. And therefore, from my perspective, it has to be that the ball of light just goes up and down and up and down. Because in my view, I'm not moving. So the ball of light has to hit the top mirror. And if it hits the top mirror from my view, it has to hit the top mirror from your view too. The ball of light cannot, therefore, fly out into space. So what therefore would happen is this. Let's put these two clocks over to the side, and let's look at that ball of light undergoing its motion in the moving clock. Diagonal trajectory up and down. Now notice something. The amount of time that passes on the two clocks is different. Why is that? Well, think about it. Look at the trajectory of the light in the moving clock. Because it's a double diagonal going up and down on the diagonal, the trajectory that it follows for it to go tick and tock, and let me show you this in slow-mo, the trajectory that it follows to go tick and tock is longer, right? So let's take a look at that. Set these guys into motion. This guy has already gone up and down. He registers 1. This guy, because he's going on a longer trajectory from your perspective, and yet the speed of light is constant, longer trajectory, it's going to take it longer to get there, which means this guy's gone tick-tock. This guy has yet to reach the top of the mirror. So if we let this guy continue on, then notice that this guy is reached 2. This guy is just bouncing off the bottom. He's far away from reaching 2. Let him keep on going, and so on and so forth. You see that the rate at which you've got time elapsing on the moving clock is slower than the rate at which time elapses on your stationary clock. And it all comes down to the speed of light being constant. The perspective, that is, from the laboratory observers, those folks who are watching the moving clock rush by, they see that the ball of light in the moving clock is still going, bouncing up and down between the two mirrors, but from the perspective of those of us in the laboratory, the trajectory which the light needs to follow to go tick-tock in the moving clock, the trajectory, the path is longer because it's going along this double diagonal trajectory from our perspective. And if the path is longer, but the speed of light is the same, that means that the tick-tocks happen at a slower rate in the moving clock. Our clock's going tick-tock, tick-tock. The moving clock is going tick-tock, tick-tock. Time itself is elapsing slower on the moving clock. So this is this wonderfully amazing idea that we have now established with this light clock, that from the perspective of those in the laboratory watching a moving clock, they will conclude that time runs slowly on that moving clock. And again, I've used the light clock as a tool, as an intermediate step, because as we just saw, I can easily see the effect of motion on the passage of time. The same would be true if I used any other clock, a Rolex, a grandfather clock, because what we're talking about is how motion affects time itself. And the conclusion is that from our stationary perspective, a clock that's in motion will tick off time at a slower rate.